Hello, this lesson is about the second fundamental theorem of calculus, part 2. So the very first video I showed you about the second fundamental theorem of calculus, we talked about, as you can see here, we talked about taking the derivative of the antiderivative. And if you have a special case where you have a function up top and a constant on the bottom, all you have to do is plug in x everywhere you see t. Okay? And if it happens to be a function that is derivable, you have to multiply it by the derivative as a result of the chain rule. Another thing that you're going to see on the AP test is the second fundamental theorem of calculus applied towards a graph. It basically is a very conceptually hard topic. It's not very difficult math-wise. So if you understand this conceptually, then you're very intelligent in calculus. So in this particular problem, you'll see it says here is a, let's say, we have this graph, and it says here's my function g of x equals 1 to x of f of t dt. And I have this graph. No function, no numbers, no exponents, just this graph. Find a couple of things for me. So let's look at question A. Question A says find g5, g prime 5, and g double prime of 5. If I look at my original problem, if I zoom in here, here's g of x. And the first question says find g of 5. Alright, so let's plug in 5 for x. And I get that. So remember, this picture is a graph of f. Let me highlight it for you. This is a graph of the function f. So if I'm trying to find 1 to 5 of f, I'm basically trying to find the area in the curve between 1 and 5. So if you notice, here is 1, here is 5. I need to find this area right here. You'll notice that this is a triangle, and this piece right here, the second piece right here, is a rectangle minus a fourth of a circle. So this is like a rectangle minus a fourth of a circle. So I'm trying to find this area here, this triangle, and this rectangle minus a quarter of a circle. This triangle, if you remember, the area is half base times height. I have a base of 2, I have a height of 4, so this whole thing has an area of 4, half base times height. The rectangle is 2 across and 8, so this whole rectangle is 8. So if I gotta subtract a quarter of the circle. Area of a circle is pi r squared, and I want a fourth of it. The radius of the circle, if you notice, goes from here to here. It's a radius of 2. 2 squared is 4. So this whole thing is just pi. So this area right here is 8 minus pi. So my answer for g5 is 4 plus 8 minus pi, which is 12 minus pi. So I found g of 5. Next part says I want g prime of 5. G prime of 5, if you remember, means take, here, I'll write it here. If I want g prime of 5, g prime, if you remember the derivative of this, if I want the derivative of that, means take x and plug into t. So g prime of 5 is the same thing as, just the same thing as f of x. Or in this case, because x is 5, it means the same thing as f of 5. So really, long story short, all I want to do is look at this graph and what is the y value when x is 5. So here is x is equal to 5. My y value is 2. So g prime of 5 is 2. So I know it sounds confusing, but remember, the derivative of the antiderivative is just plug in 5 for x. If I plug in 5 for x, my y value is 2. And lastly, I want g double prime of 5. G double prime of 5, if I show you here, means I really want f prime of 5. Okay, so if you understand, let me highlight this. If you understand g of 5 is just plugging in 5 into the antiderivative. If you understand g prime of 5 is just plugging 5 into f of x, you should understand g double prime of 5 is just plugging in 5 into f prime. So again, I go back to my graph. Essentially, what is the slope at 5? If I look at this, I'll use a different color. I notice that at 5, I have a slope, a flat line of 0. So this one is 0. Okay. B, same thing, just if you understand it, can you find g1, g prime 1, g double prime 1? All right. G of 1, again, is equal to, the constant at the bottom is 1, to 1 of f of t dt. You may notice that my bounds are exactly the same. So I forgot if I taught this to you, but if you have a case where the bounds are the same, there's no area under the curve. I mean, it's like going from here to here, like it's the exact same. So this is 0. G prime of 1 means, again, taking 1 and plugging into here. So G prime of 1 means the same thing as f of 1. I look at my graph again. When x is 1, my y value is 0. If you have a hard time seeing it, let me erase this. When x is 1, my y is 0. So this one is also 0. And the last one, g double prime of 1. G double prime of 1 means the single derivative of f of 1. If I go to 1, you'll notice that I need to find out the slope of this line. This slope is over 1 up 2, so it has a slope of 2 in this line. So this answer is 2. Again, not very difficult in the math, but very conceptual. Do you understand what's going on in the second fundamental of calculus? All right, a few more questions. It says find the values of x in the open interval at which g has a relative minimum. To find where we have a relative minimum, remember you take the derivative and set it equal to 0. So g of x is equal to 1 to x of f of t dt. So if you remember min and max, this is a nice review. Take the derivative, set it equal to 0. The derivative of this, remember, is just plugging in x. So the derivative of x is f of x. To find the relative min and max, I need to set this equal to 0. If you remember, mins and maxes. Mins have a derivative that go from, first they start down, and then they go up. So basically, I'm trying to find where f of x is equal to 0, and where do I go from negative to positive? So let's go back to my graph. Let me erase all of this. Here's my graph. And let's figure out where f of x is equal to 0. F of x is equal to 0 here, here, and here. This is where f of x is equal to 0. Okay? Now, where do I go from negative to positive? Here, I go from positive to negative. Not slope, just the value. The value is positive, now the value is negative. That's a max. This one I go from negative to positive. And this one I go positive, I don't have anything other words. So this is the only place where I go negative, 0, then positive. My relative min is at x equals 1. This one says find the absolute maximum value of g. All right. Absolute max is the same thing as relative min and max, but then I'm going to try to find the biggest value. Okay? So if you remember absolute value, absolute max versus relative min and max, same thing. I take the derivative, which is f of x, set it equal to 0. I need to go from positive to negative. I go from positive to negative here, and possibly there. Okay? Remember, in absolute max, min, and max, it could occur at any of these points, this point, or this point, or at the endpoints. Remember, my endpoints are negative 8 and 8. So I have a couple of numbers to test here. Okay? So the question is, how do you know which one's the absolute min, or how do you know which one's the absolute max? If you remember, so basically I have a couple points to test. Negative 8, oops, negative 8, negative 7, and 8. These are my possibilities. If you remember how to do absolute min and max, what I did is I plugged these into the original function and see which give me the biggest number. Okay? So g of x, if you remember, is equal to 1 to x of f of t dt. So all I'm going to do is plug in negative 8, negative 7, and positive 8, and plug that into this bound and see which one gives me the biggest value. For sake of time, I won't do it completely. Like, I'll show you how to do this, like 1 to negative 8, 1 to negative 7, 1 to 8, and see which one gives me the biggest number. First of all, going from 1 to negative 8, I'm going basically Let me erase this. 1 to negative 8, I'm getting this and this, right? 1 to negative 8, that's the area. And remember, since I'm going backwards, this becomes positive and this becomes negative. So I got a pretty big area. You'll notice that this piece right here and this piece right here cancel each other out. So this area right here is 1 to negative 8. This is 1 to negative 8 area. Okay. If I calculate it, the area of a trapezoid, if you remember from the last video, is average of the bases times the height, or times the height. Yeah. My height here is 2, and my bases are 0 to negative 7, so 7, and the bottom base is 1, 2, 3, 4 over 2. This is 11. So if I plug in negative 8, I get 11. Okay. If I plug in negative 7, I'm going from 1 to negative 7. If I erase what I just did, I'm going from 1 to negative 7, which is here, all the way to just here. So now you notice that this is a way bigger trapezoid than the last one. So same thing, the height is 2. Average of the bases, I have a base of 1, 2, 3, 4, and a base of 8 over 2. This particular one is an area of 12. So far, this negative 7 is winning. And then if I do 8, do you remember 1 to 8 is this right here? It's going to be positive because I'm going in the right direction, left to right. From 1 to 8, I've got a triangle, and I have this rectangle right here minus a circle. This triangle, half base times height, I have a base of 2 and a height of 4. So this is 4 from last time. The right triangle, half base times height, 1 times 4, this one is 2. This one, I have a rectangle of 4 times 4, I have 16. That rectangle is 16. And I subtract half a circle that has a radius of 2. So 16 minus 2 pi. This is about a little bit less than 10, or about 10, right? So if I plug in plug in negative 8, I get 11. Plug in negative 7, I get 12. I plug in 8, I get 10. My absolute maximum has to be negative 7. And the last question says, where are my points of inflection? What do you know about points of inflection? Points of inflection are when the double derivative or I'll do second derivative, you set it equal to 0. Okay? So let's do this again, just to refresh your memory. G of x is this little thing. G prime of x is just plugging in x for f. G double prime of x is f prime of x. And I need to set that equal to 0 to find my points of inflection. So basically, I'm trying to find where in this graph is my slope equal to 0. So let's go back to my graph. Let me erase all this mess. Okay. I'm trying to find where is my slope equal to 0. I've got a slope of equal to 0 here. I got a slope equal to 0 here. Oh, sorry. Also, inflection points can happen when the derivative doesn't exist, which happens at here, here, and here because they're corners. If you remember, corners or these sharp turns also count. So my inflection points are negative 7. This one, because it's totally flat, I don't necessarily have an inflection point for the whole thing, but I will have an inflection point. Oops. I will have a inflection point here and here. So inflection point negative 7, inflection point negative 4, inflection point 0, inflection point 3, inflection point 5, and inflection point 7. So, long story short, you have 6 inflection points. Okay? So hopefully you understand this topic. Again, it's a very conceptual process, not very much math. We're still applying the second fundamental of the theory of calculus, but this time to a graph. And the second page is the same thing, same graph. See if you understand this. You will get a question like this possibly on the free response. So hopefully you understand. And again, we'll spend some time in class to answer any questions that you have. If you are confused, please put it down in the quiz so that I can help you out the next day in class. Hope you understood, hope you enjoyed the video, and I'll see y'all later.